You know those sleek curves on a modern car? Or the enormous, powerful wings of an airplane? Well, they don't start out as clay or metal. Nope. They begin as pure information inside one of the most powerful digital design tools on the entire planet, CATIA. Today, we're going to crack open that virtual workshop and see exactly how it's all done. It really all boils down to one fundamental, high-stakes question. How can you build a plane, or a car, or even a critical medical device, and be absolutely sure it's safe and strong before a single physical part has ever been made? Well, the answer's all about transforming design from a hands-on craft into a digital science. And to really get why that science is so critical, we first have to understand the incredible pressure that modern designers and engineers are under every single day. I mean, think about it. In today's world, it's not enough to just make a great product. You've got to make it better, you've got to make it faster, and you've got to make it cheaper than anybody else on the planet. This constant race puts a huge strain on the old ways of doing things. You know, building physical prototypes, testing them till they break, then starting all over again. You just don't have the time for that anymore. And this is where our digital workshop comes into play. This is the environment where engineers can build, bend, and even break their creations 1,000 times over, all without ever leaving their computer. So at its core, CATIA V5 is a computer-aided design platform, or CAD for short. But, that's kind of like calling a space shuttle a vehicle. It's so much more. It's a complete virtual environment where the most complex products in the world are literally born. It's one part digital sculpting studio, one part engineering lab, and one part assembly line, all rolled into one incredible piece of software. Okay, so how do you actually create those incredible flowing shapes we see on everything from a sports car to a jet engine? It's not like you're just stacking digital bricks. It's way more of an art form. The magic happens in a special area called the Generative Shape Design Workbench. Here, designers aren't just drawing lines. They're creating these intelligent relationships between points and curves. So if you change one curve, every single surface that's connected to it automatically adapts. It lets them sculpt these mind-bendingly complex forms that would be just impossible to create with simple geometry. And the process is just brilliantly logical. First, you create the wireframe. Think of it as the digital skeleton, right? The basic curves of your object. Then, you stretch a digital skin, that's the surface, right over that skeleton. And finally, once that shape is absolutely perfect, you tell the computer, okay, make it solid. Skeleton, skin, solid. That's how you go from a simple idea to a virtual, tangible part. But hold on. A modern airplane or a car can have literally millions of parts, surfaces, and wireframes. Creating them is one thing, but managing that insane level of complexity, that's a whole other challenge. The key to taming all this chaos is something called the specification tree. You can think of it as the master blueprint, or maybe even the DNA of the entire model. Every single thing a designer does is recorded right here. Every step, every feature, and exactly how they all connect to each other. A clean, logical tree means you've got a design that's easy to understand and, more importantly, easy to change later on. And to manage this tree, designers have two main ways of thinking. A geometrical set, or GS, is like a creative brainstorming whiteboard. It's flexible, it's forgiving, you can move things around, reuse bits and pieces for different operations. But an ordered geometrical set, or OGS, that's more like a formal step-by-step assembly manual. Everything is locked in the exact order it was created. And once an element is used, it's consumed, meaning it can't be used again. It's done its job. Sometimes you need that creative freedom, and sometimes you need that rigid, repeatable process. But creating the perfect shape is really only half the battle. Now, you've got to make sure it can actually survive in the real world. And this is where CATIA transforms from a design tool into a virtual proving ground. This right here is the absolute game changer: design integrated analysis. Instead of finishing a design and then tossing it over the wall to a separate team of specialists to test, the designer can run incredibly sophisticated simulations right inside the same software. They can apply forces, heat, vibration, all to their virtual part and see instantly how it's going to react. And this visual just illustrates the result perfectly. On the left, you've got the original design. On the right, the analyzed and optimized structure. Now, those colors aren't just for show. They represent stress. Red is basically the computer screaming, high stress here, this needs to be stronger, while the blue shows areas where there's very little stress, places where engineers can safely remove material to save weight, which is absolutely critical in aerospace and automotive design. And hey, don't just take my word for it. Check out this quote from a project leader at Honda. He's saying that for a super complex gear assembly, a process that used to take days and require a team of specialists can now be set up by the designer themselves in just 30 minutes. That kind of speed is absolutely revolutionary. So, what really happens when you merge the world of design and the world of analysis into one single, seamless process? Well, you fundamentally change what is even possible in engineering. The benefits are just enormous. I mean, you're designing and analyzing in one place, which means you can try out new ideas almost instantly. This lets engineers consider way more options, which leads to more innovative and, frankly, better performing products. And of course, it massively cuts down on the need for expensive, time-consuming physical prototypes. You get it right in the digital world first. Which leaves us with one last big thought. We've seen how this tech lets us build better cars and safer planes today, but what about tomorrow? When the line between creating an idea and testing its limits completely disappears, what new frontiers of innovation does that open up for us to explore? What becomes possible then?